Quantum computers, they hold this incredible promise of solving some of the world's absolute biggest problems. We're talking about designing life-saving drugs in a heartbeat, or discovering new materials that could completely revolutionize energy. They could give us these exponential speed-ups that would literally change the world as we know it.
But, and it's a big but, here's the catch. The quantum hardware we have right now is nowhere near perfect. It's what everyone in the field calls noisy. These machines are just so sensitive that tiny, tiny errors build up like crazy, and they can completely wreck a complex calculation. So that leaves us with this massive looming question. How do we actually use these things? How do we bridge the gap between this amazing potential and the messy reality of today's error-prone machines?
Okay, to get our heads around this, let's just look at a simple timeline. Right now, today, we are firmly in the noisy intermediate scale quantum era, or NISQ for short. And yeah, it's a pretty tough place to do calculations. The next stop on the roadmap is the early fault-tolerant era, or EFT. And the ultimate dream, the end goal, is the fully fault-tolerant, or FT era, where errors are basically a solved problem. Our entire story today is about how we get from here to there. To really understand the solution we're going to talk about, we first have to appreciate just how big the problem is in this noisy quantum world. So look at this number. This is the typical physical error rate for just a single quantum operation in one of today's machines. Now, I know, it looks super small, right? Almost nothing. But here's the thing. When you're running a circuit with thousands, maybe millions of these operations, these tiny errors compound. They stack up. And they very quickly turn your beautiful quantum calculation into completely useless garbage. Without a really clever strategy, you are dead in the water. And that clever strategy, our hero for this explainer, is the Variational Quantum Algorithm, or VQA for short. It is a brilliant workaround that was designed specifically for this noisy era.
So what on earth is a VQA? Well, think of it as a powerhouse team-up. It's a hybrid algorithm. It combines a simple, shallow quantum circuit, that's a circuit that's short enough so it doesn't get completely destroyed by noise, with the good old-fashioned power of a classical computer. The classical computer's job is basically to train the quantum circuit, to guide it toward the right answer by learning about and working around the noise in the system, instead of trying to make the noise disappear, which is just impossible right now. This whole partnership works as a feedback loop. You can almost think of it like a teacher and a student. The classical computer, that's the patient teacher. And the noisy quantum device is the brilliant, but let's say sometimes erratic student. The teacher gives the student a problem, checks the work, and then gives feedback to help it get closer and closer to the right answer again and again. All right, let's break that loop down. First up, the classical computer makes a guess for the settings, the parameters of the quantum circuit. Then the quantum computer takes those settings and runs its short little program. Next, we measure the result that comes out and we give it a score based on how good it is. After that, the classical computer looks at that score and says, okay, let me make a smarter guess for the next try. And finally, we just rinse and repeat this process over and over until we've cranked up the score as high as it can go and found our solution. Now, this sounds fantastic, right? But VQAs face a huge and frankly super weird challenge of their own. It's a problem that's unique to the quantum world, and it's known as the barren plateau. To wrap your head around this, let's use an analogy. Imagine training an algorithm is like you're a hiker trying to find the absolute lowest point in a huge hilly landscape. This landscape is your cost function. It's just a map of how good your answers are. To find the lowest valley, which is the best solution, all you have to do is look around and always walk downhill. The steepness of the hill, what we call the gradient, tells you exactly which direction to go. Simple enough? A barren plateau is the quantum version of our hikers suddenly finding themselves in a perfectly flat, featureless desert that stretches for miles in every single direction. The gradient, the steepness, it just vanishes. It's gone. There are no hills, no valleys, no slopes, nothing. The optimizer has absolutely zero information telling it which way to go, and the training just grinds to a complete halt. And this comparison really drives the point home. In a normal landscape, you can optimize because you have features to guide you. But on a barren plateau, it's pretty much impossible. This is a bizarre consequence of the mind-bogglingly vast base of quantum states and all the complex entanglement between the qubits. And what's worse, it gets exponentially worse as your quantum computer gets bigger, which makes it a massive roadblock for scaling up VQAs. But the good news is researchers are finding some seriously clever ways to avoid these quantum deserts. By designing the problem differently, by focusing on little local parts of the system instead of the whole shebang at once,
And just by being smarter about where we start our hike, we can often find a path around the barren plateaus altogether. So here's the crucial point. The VQA isn't just some temporary trick for the noisy era we're in now. No, it's an idea that is actually evolving to stay relevant as our quantum hardware gets better and better. Let's see how. Okay, so as we move into that next era, the early fault-tolerant era, we'll finally start to have some error correction. But it's going to be extremely expensive to use. So we'll probably use a strategy called partial quantum error correction, or PQEC. The idea is, instead of protecting the entire computation, we'll strategically protect only the most sensitive bits, giving us the most bang for our buck. And this kind of picky, strategic approach is a perfect fit for VQAs. And VQAs are just perfectly suited for this. The whole framework is flexible enough that we can adapt it to use these new error correction techniques. The VQA can literally learn to balance the need for more accuracy against the high cost of using these error-corrected operations. In other words, the VQA itself is becoming resource-aware. It's adapting to the very hardware it's running on. So let's bring all this together. We started with a noisy problem, we found a clever hybrid solution, we tackled its biggest challenges, and we saw how it can evolve. What does this all mean for the real world? Why should you care? Well, because VQAs are not just some theoretical curiosities stuck in a lab. They are being actively developed and applied right now, today, across a huge range of really important scientific and industrial fields. And we are talking about tangible, real-world applications, things like using VQAs to design new drugs and materials in quantum chemistry, solving unbelievably complex optimization problems that are just impossible for classical computers, impacting everything from global shipping to financial markets, building the next generation of artificial intelligence with quantum machine learning, and even simulating the fundamental laws of physics to unlock the secrets of our universe. That's why this matters. You know, this quote from the source material really sums it all up perfectly. VQAs were born from the limits of our current noisy hardware, but they are not destined to become obsolete. In fact, as our quantum computers evolve, VQAs can evolve right alongside them, finding a new and even more powerful role to play in the future. Which leaves us with a final thought. We started with the massive promise of quantum computing, a promise that's been held back by all this noise and all these errors. We've seen how this brilliant partnership between classical and quantum machines can tame that noise today and adapt for tomorrow. So the question now is, will this be the essential bridge that finally gets us from today's fragile hardware to that revolutionary quantum future we've all been waiting for?